Hello and good morning, good evening, or good night, wherever you are. It's my pleasure to present my paper, Co-Evolution of Initial Configuration and Control in Evolutionary Robotics. So my name is Kasper Stoy, and I'm a professor at the IT University of Copenhagen. I was lucky to get one of these large spots here with 25 minutes, so I think my talk is structured around a 5-minute perspective on evolutionary robotics, and then I'll dig into the specific contributions of this paper. So if we look at evolutionary robotics from a helicopter perspective, then we can see in the early start, there was really a great excitement. We could evolve controllers instead of programming to avoid human error and bias. And I think you can see this in a lot of the papers. There was this excitement that maybe in the future we never need to program. It's much better just to evolve controllers. And then as time progressed, we sort of stumbled upon the challenges that we know very well today. So maybe some of the prominent ones are reality gap, limitations of simulations of robot, the size of search space for complex tasks, and so on. And you would think that we kind of continue to push through these things to sort of realize this idea of evolving controllers for actual physical robots doing real things in the real world. But actually, a lot of these challenges turned out to be so hard that we kind of diverged a little bit and started to into this more theoretical realm. So sort of digging in and starting to solve part of the problems and maybe losing a little the original idea behind evolutionary robotics research. So if we look at the history, again, in a little more detail, I think it's also evident that a cost of this development is complexity. So of course, it's clear when you have a problem where simple approaches, one can discuss evolutionary computation is simple, but in the beginning, if simple approaches doesn't work, then you go through this process of complexification, because you have the general method, and then maybe if you add something, then you can solve specific limitations of the original problem. So it's sort of a natural scientific concept that solutions complexify over time to try to attack this really hard problem, which is evolutionary robotics. So here's some example papers you can see in the beginning. Maybe this is actually not quite the beginning, but we, at least in '96, talked a lot about the evolution of controllers, obstacle avoidance, simple things. And of course, we then quickly talked about, oh, this is hard. This can be done, but it's hard to develop more complex behaviors. So relatively fast, we start talking about incremental evolution. So evolve behaviors stepwise, sort of to get to a higher level of complexity. And of course, we're somewhat successful. Then later, maybe with the role of embodied AI and so on, people start to think about, okay, maybe if we evolve the morphology and the environment, sort of stepwise making it harder and harder, we can make our robots work better and better. And then maybe a current big paper is kind of these POET algorithms, where we talk about evolving the environment and generating whole new environments that sort of creates these steps that allows an agent to learn complex tasks, and also maybe tasks that are more complex than envisioned by the researcher. I mean, this is part of this AI mantra, I guess you can say. But again, these algorithms to the right are starting to get more and more complex. So you have to encode morphologies, you have to encode environments. There's a complexity, there's a runtime complexity cost. It takes a lot of computational resources and so on. And frankly, there's not a lot of robots. It is often done in simulation, of course, because of reality gap and other problems. So this is why I'm saying that of course this theoretical work has high value. It's important, but maybe also sometimes it's not addressing the original problem of trying to control real physical robots. What if I just want a controller for a given robot task and environment? I mean, I have a robot in my hand. I know what I want to do with it, and it has to be in this hospital floor. I'm not sure many of our modern approaches help us so much here. So this is why I'm sort of returning to this now ancient robotics, evolutionary robotics research, because I think this is where the simplicity is, and maybe the applications are in the end. So the idea I got during Corona, being at home a lot, you get to think, which is not always good, but sometimes it is. And basically the idea that occurred to me was that learning in biological systems, in particular humans, works a little different. So if we look at these nice pictures of babies, we can see that parents place children in these configurations in the task environment that facilitates faster learning. So maybe on the right, the baby is put in a position where it's almost already walking by the parents. So we're holding the hands, we're putting it upright, and then it can take the first stumbling step. So basically we're putting in a position where the opportunity for learning are greatest. Similarly, on the left, we basically constrain the whole body to make sure that the focus is on the eating and the mouth, and not about falling down from chairs and crawling around on the floor, right? So we limit, I think in computational terms, the search space for the child, for the learning agent here. So basically, if you talk about evolutionary robotics, we are not really evolving the task or the morphology or the environment. We just figure out in which configuration to start the learning process. So once you have this simple idea, you can talk about the context of evolutionary robotics. Of course, we still want to evolve a controller. That's our aim. We have our evolutionary algorithm. But now it's not a matter of where in the environment, now it's not a matter of evolving the environment. Now it's the environment is given. So where should we place an agent in the environment so that it can learn the most? Similarly, it's not about developing new robot bodies. It's about having a robot with a specific configuration of legs. How should the legs be placed in order to learn faster? So should you start standing up? Should you have slightly bent knees? Should your arm be out? How is this? Similarly, also it talks about in which task configuration should you start learning. So maybe if you are evolving for robot soccer, maybe in the beginning you should have the ball very close to the goal and opponents far away, and you can change this task configuration as you move forward. So this is one of the main points of the paper, to try to think about not encoding all these environments or morphologies, but thinking about what is an intelligent way for the learning system, or an intelligent configuration to start into to facilitate faster learning. So this paper is a simple, very, perhaps to a bit, pinprick attempt at addressing this overall research agenda. So in this paper, we'll talk about where in the environment. And for our task, we are again back in history. So I use this old obstacle avoidance of mobile robotics as a base case, simply because everybody is aware of it. And of course, also the simplicity part is of course also important because of the reasons I mentioned earlier. So in their case, they had a little mobile robot in an arena that was moving around. They had a simple neural network, 8 sensors going into some hidden units that then activated the wheels directly. There were also a few recurrent neurons here, recurrent connections, and they had a sigmoid activation function. So a classic obstacle avoidance evolutionary robotics setup. We do exactly the same. So we reproduce basically their experiment. For instance, there's a fitness function that rewards, so V is velocity, so the average velocity of the wheels, saying that we should move as fast as possible. This guy talks about the difference between the wheel speeds and prevents the robots from wanting to turn on the spot. That's perfect obstacle avoidance strategy, of course, if we don't prevent it in the fitness function. And the last term talks about sensors. You should have as low sensor input as possible. So this is sort of a classical fitness function for obstacle avoidance. And all the other parameters are sort of kept and are maybe not super important. What is important is the arena itself, because I've chosen a very challenging version of the problem where it's an empty square arena, which is 8 by 8 meters. So the robot is 10 centimeters and the arena is 8 by 8 meters. So this is the given environment, and there's no way around that. And then for initial configuration, I placed the robot randomly orientation and position in this environment. And as one may expect, the robot evolutionary computation works. The evolutionary works. I get high fitness, and you can see here the results of the averages of 25 runs. But actually, then when you look at the behavior of the robots, this is maybe a little complex, as my reviewers told me. So basically, the arrows here are the starting point of a robot, and then the trail is the movement of a robot in the last iteration of the evolutionary algorithm, and X marks where it ends. So we can basically see that all the 25 best individuals, if they happen to encounter a wall, they crash. So they have not learned obstacle avoidance. And why not? And it's, of course, the intuition is fairly clear. It's really difficult for individuals to encounter obstacles. So it's sort of a rare occurrence. And if they do encounter an obstacle, it leads to low fitness compared to the ones who does not encounter an obstacle. So they are immediately eliminated. So there's basically no way the system can ever learn obstacle avoidance in this environment. And I think this is also some result that should have been published 30 years ago, saying that, you know, these obstacle avoidance evolution only works in very restricted environment, because the robot really need to be forced to be close to walls at all times. I did more tests on this and then find that actually if the arena size, the side length is less than 3 meters, then evolution does work. So in this case, we can actually evolve obstacle avoidance. So there it balances out. You need the wall often enough that it actually guides evolution in the right direction. So I also tried various other configurations just to see. I mean, I really wanted to work in this environment. So I tried a system where robots face the wall from the beginning, because that's the difficult one. But of course, evolutionary computation is great. So it finds a solution that is that the robots always learn to reverse. So basically here it's a lack of coverage. I mean, I don't sample from the entire configuration space. So therefore the robot can learn to overfit and exploit this situation. I also tried to put the robot close to the wall with a random orientation, at least increasing the probability that it would encounter the wall. But again, it fails for the same reason as the original experiments, because individuals that are facing the walls are eliminated. I mean, they crash immediately, whereas the one that are facing away from the wall generate a lot of fitness and get selected. So basically here the problem is noise again. The orientation decides your fitness basically, and there's no way to differentiate the individuals. So as an overview, if we talk about how to choose these initial configuration strategies today, we can do random, as I did in my initial experiment, and that encourages that there's coverage of the configuration space, and it prevents overfitting. But of course, it's hard to differentiate individuals. I mean, in this case, they're all away from the interesting stuff, so we can't figure out which ones are the good ones. And of course, there's also a lot of noise. The fitness almost only depends on the placement of the robot once it's learned to drive straight. You can also do fixed configuration. This is often used here. It's easy to differentiate. They all compete on equal terms. And of course, there's also no noise introduced by the placement because it's the same. But then again, you have a coverage problem. Well, how do you know it can solve the problem if it started in other situations? And of course, it tends to overfit and exploit the situation. You can do something with random configuration where you sample more times, but again, then you sort of run up this hill of increased complexity. So, but this is the simple picture here. So the simple idea I had here, based on the child, was to use co-evolution. So basically, now I have a population of controllers, and I also have a population of starting configurations. So where should the robot start in the environment? And the representation is simple. So X, Y, position of the robot, and the orientation. And the fitness of a configuration is basically 1 minus the fitness of the controller. And then I evolve them in a classic co-evolutionary setup where the individuals for one population is evaluated together with the best individual from the other population, and then vice versa. And then you get this hopefully arm race going of configuration versus controller. And we actually see this. So when we run the evolutionary algorithm, we can see that the system converges, of course, at a lower level, because now we have a co-evolutionary pressure that makes the configuration as hard as possible for the controllers to solve. And when we see the same graph again, so we can see the black arrows are the starting positions. And here it's clear that the evolutionary process have put the starting position close to the wall, because that's the most difficult for the controllers. But the controllers learn to deal with it. So we can see that the robots often start close to the wall, for instance, down here, but then learn to back away and end up away from the wall. There are a few failures like here, maybe a few more, but in general, the solutions are found. So if we look at the comparison here, again, a little simple, there's more to be said here, but just saying that co-evolution actually works here because in differentiation, I mean, we only have one configuration per generation. So all the robots are compared on the same position orientation in the environment. So it's relatively easy to distinguish the good from the bad, so to speak. We have coverage because even though we couldn't only have one configuration per generation, then if there is another configuration somewhere, the evolutionary process can move the robots around as they want over generation. It prevents overfitting. So if a robot is close to a wall, then and starts to exploit some position, then of course the co-evolutionary process will find a new configuration that's different. So basically prevents this overfitting. Again, it reduces noise. So if the robot's controller is not able to solve a problem, it would be started in that position until it manages to solve the problem. And then again, the co-evolution process may find a new configuration for the robot to be moved to. So this is my final slide. I think there are some open issues and lots of discussion of these ideas. So of course, I'm only starting here. Luckily, COVID didn't last so long, so I went back to my professor job. But if we look at the co-evolution of initial configurations and controllers, it would be interesting to look at this reduction of evaluation times. I mean, I think there's something fundamental if you're starting to learn. I mean, maybe it's more productive to start in a configuration later in the process where you're just about to fall, because maybe the controllers that can handle that would be the best. So basically, this could allow us to reduce evaluation time to a very short period for in specific kinds of tasks. Reduce number of generations, the same argument. If we have more efficient learning, then of course we may not have to run our evolutionary processes so long. So there's sort of a cheapness here. Then on the downside, you can say we haven't solved everything. There are many limitations to the approach I'm happy to discuss. But one of them is it's the devil's advocate co-evolution that is choosing this initial configuration. So this means that if you have a giant soccer field with robots placed around, then the configuration co-evolution would find is probably something where the ball is just about to pass the goal line of of your own team, preventing forward. So basically, it's hard in the current setup to do something for a very complex task. Of course, there are some, of course, in ProIt, for instance, the algorithm, there is something about how to find these configurations at just the right level of challenge. And I think this is probably where it should go. But again, I'm a little wary about this slippery slope of complexity. So, I mean, how much complexity do we add to get to this point? But it's worth a try and see if a simple dictionary of configurations could help sort of make sure we have configurations of the exact right challenge for the robots. Good, so this is a conclusion overview. So I started with an academic rant about complexification in evolutionary robotics and sort of the external drivers maybe of the research, just to give people something to think about. I think there's benefit to all kinds of research, but maybe there's room for people to think about whether they can do something different and it will better fit other people than currently are. So the specific contribution, very small idea of co-evolution of initial configuration and controller that actually seems to work in this simulated environment. Of course, I'm not proud of this as a roboticist. It would have been nice if I had a robot can do it on the physical system too, but that's okay. And then finally, I think maybe this is where the meat is. I think it's a general contribution, this choice of initial configuration. I think there are some mileage in this that could be open for further exploration, and it's a fairly simple idea. I'm sort of excited to see how far that can go. That ends my talk. Thank you for waking up or staying up to hear the talk. And of course, I'm very sad I cannot be there in Prague with all of you and have a nice Czech Pilsner. But I guess that will have to be next time. Now I'm happy to take questions.